this is where the calculation of the unit cell volumes are going to take place. So let's take a face-centered cubic crystal structure. We take our hard sphere model. So it has a unit cell, and so with the reduced unit sphere model is going to be a little more the common way that we're going to visualize an FCC unit cell. So we know that we have an atom at each corner, and then we have one on each face. And so in order to really start to determine that volume, there's a couple things that we need to take into account for first. As we said, this unit cell is the Lego. And so with that Lego block, let's say we want to build a larger structure. Now, if we look at each of these corner atoms and we start thinking of how we can stack cubes around it, we can stack 8 cubes in contact with each corner. So there are 8 other unit cells that are sharing this one atom at each corner. So what we say is that if we're looking for the number of atoms that are associated with a given unit cell, 1/8 of each of these atoms belongs strictly to this unit cell because it's sharing that atom with 8 other unit cells, or I should say 7 other unit cells. So it owns 1/8 of it, and it owns 1/8 of each of these. If we look at the corners, it's a cube, there are 8. So 8 times 1/8 gives us 1 atom. Now, each of these ones on the face is only shared by 1 other atom, or 1 other unit cell. And so the 6 faces that we have corresponds to 3. So 6 times 1/2, because this unit cell owns 1/2 of that atom, gives us the 3. So the 1 from the corners to the 3 on the faces gives us 4 atoms assigned to each unit cell. It's going to become important when we start going a little further. So let's think a little more about this FCC crystal structure. So we want to figure out what the actual volume of the crystal structure is. And so knowing that there are 4 atoms, we're going to need to know that atomic radii now in order to understand that. This is sort of where that hard sphere idea comes back in. So let's break apart that unit cell a little bit and figure out what dimensions we can actually measure. The dimensions that we can measure are only in those orientations where the atoms are touching. And so that way we can assume that across this point, we have 1 radius, 2 radii, 3 radii, 4 radii going across this diagonal. So we're pretty fortunate here. We know what the lattice parameters are in terms of A for each atom. And we know this value, and we know the A and A, the 2 A's are equal. We can figure out the volume of this just using Pythagorean theorem. And with that, we know that it's a cube, so the volume is just A cubed. And if we define what A equals to on this, for this basically right triangle, we can determine the volume. And if we work our way through, we see that the volume of an FCC unit cell is 16 r cubed times the square root of 2, based off that. So if we know the A, we know the atomic radii, we can figure out the volume of any FCC unit cell. Now, this is where that number of atoms comes in, because we know we have a certain volume of that unit cell, but how tightly are the atoms packed in it? How much free space is in there? And so with that, we can calculate an atomic packing factor, which is basically the volume of the atoms in the unit cell over the total unit cell volume. So we've calculated that total unit cell volume for the FCC. And since we're assuming hard spheres for each of the atoms, we know the volume of a sphere. Now we know that there are 4 atoms per FCC unit cell. And if we think about that, the number nearest neighbors in that is 12. So that's where that coordination number comes in. And so we can get the volume of the atoms in the unit cell is just 4 times that. So we know what that is. We know what the volume of the unit cell is from our previous one. Fortunately, we see that our R's cancel out. And the number to remember, and if I were you, I would highlight it and really note it, is the atomic packing factor of FCC. And FCC is what we're going to consider a close packed crystal structure, is 0.74. Very critical number to know, and I recommend that you keep it close at hand. Now let's move on to a body-centered cubic. So we have a hard sphere model, once again, for the body-centered cubic, and in this case, we know that the reduced unit cell, a lot fewer atoms sitting in this one, because we have the 1 atoms at each corner and then only 1 in the middle. So we know from the face-centered cubic that each of these atoms is shared with, there are 8 other unit cells that share this. So this atom gets 1/8 of that atom on each corner. We know there are 8 corners, so that equals to 1 atom. But what makes the body-centered cubic different is it wholly owns that atom in the middle. It doesn't share it with anybody else. It gets a little selfish here. So the 1 from the corners, 1 in the middle. So there are only 2 atoms assigned to a BCC unit cell. So now we're starting to see that we don't have quite the close packing that we do in the FCC unit cell. So let's think about the volume of the BCC unit cell. And if we think about the what we had with an FCC unit cell, we had each of those faces. So each of those faces gave us a pretty quick way to determine what that value of A was, or that lattice parameter. Because the BCC is not close packed, we don't really know how far these atoms are apart. So we need to find where the atoms are touching. And in order to do that in a BCC unit cell, they only really touch along this NQ value, or going through the middle. And so what we need to be able to do is solve for a pair of triangles. So we know that this NP value is for the most part this NOP. We know that A, and this value. So we know what the NP distance is. So we're going to need to know that in order to calculate what the NQ value is. And so we can work our way through, but we see that the volume for the BCC unit cell is much different. This 64 R cubed over 3 to the 3 halves. And all this comes about is because these atoms are not touching along every orientation as we had with the FCC, primarily because the BCC crystal structure is not close packed. I'll repeat that, BCC is not close packed. And so we can figure out the atomic packing factor, and we see that this lack of close packing comes out to an atomic packing factor of 0.68. We see a much lower coordination number. We see fewer atoms per unit cell. So atoms in a BCC crystal structure just are not packed as closely as they are in an FCC crystal structure. It's going to give us differences in densities and different components like that. Now, the hexagonal close packed crystal structure is much more complex. It involves a hexagon. And what we're going to typically see here is that each of these top and bottom faces have 6 atoms. They're forming a hexagon. It's in the name. Mid-plane, there are 3 additional atoms per unit cell. Now, if we start breaking up the hexagonal close packed, we see that it matches that in its name. It's hexagonally close packed. FCC, or the face-centered cubic, is also a close packed structure. So in both of these, the units, the coordination numbers are going to be identical, as is the atomic packing factor. But the difference is in the volume of a unit cell for the hexagon is we're going to need to know both A and C. So in this type of ideal situation, we see how C, for the lattice parameter C, or the height, is different than A. And we can calculate the volume. We're not going to run through that. It becomes a little more of a complex geometric problem. But what to take away about HCP? It's close packed. It has a coordination number and atomic packing factor that are the same as FCC. This 0.74 atomic packing factor and a coordination number 12. BCC is not close packed. So it has a coordination number of 8 and atomic packing factor of 0.68. So some numbers to learn. Now, we've sort of rigorously defined crystal structures for individual elements. Not all elements are really happy with remaining the same crystal structure from liquid to solid. They will change crystal structures, and some metals have more than one crystal structure. It's going to depend on temperature and external pressure. So some of them can change even within at the same temperature and pressure, can exhibit different crystal structures. This is called polymorphism. What we typically see that's much more common is allotropy. And this is different crystal structures can exist in different elemental solids at different temperatures and pressures. I have 2 common examples here. Is iron. Iron really cannot make up its mind. At room temperature, iron is BCC. It's raised to about 912 degrees C. It converts to FCC. and then you raise it up to 1400 degrees C just prior to melting. It converts back to a BCC structure. We take full advantage of this with iron. It gives us a lot of the qualities of steels that we're going to be talking about later on in the course. Titanium as well. It goes from HCP at room temperature. You raise it above a temperature of about 882 degrees C, it becomes BCC. So it has a high temperature phase. And so these are what we consider allotropic phase transformations. They're pure elements. There's no change in composition because they're pure. There's no way to change the composition. They just change crystal structure with temperature and or pressure. We just never really take pressure into account. But with changes in temperature, we see these changes in crystal structure. Very critical ideas to really take into account, and we're going to take full advantage of this as materials people. Now, what happens with crystal structure to compute density? We can compute the theoretical densities of these because we know the volume of the unit cells that make them up. So if we know the number of atoms associated with the unit cell, we know the atomic weight, we know the volume of the unit cell, we know Avogadro's number, we can theoretically calculate density. Let's think of copper. And we can do this for pure elements. We know copper is FCC. We go back to our tables. We see what the atomic radii is, and we know what the atomic weight is just from our typical periodic table. So we know what that equation tells us. So if we plug and chug through that of everything we know just fundamentally about copper, from 4 atoms per unit cell based on its crystal structure to its atomic weight to the volume of that unit cell because it is an FCC structure, to Avogadro's number, we can come up with a value of about 8.89 grams per cubic centimeter. If you would go into the literature, it comes out to be 8.94. That is pretty close for just a pretty common area. So one of the things might be that we could consider that the difference would be the difference in atomic weight, or the difference that we might see in a couple other components like the atomic radii may not be exactly the same. So you start thinking about it, that is pretty good way of just with minimal value figuring out what the density of a part's going to be. And when you start thinking about weight and weight savings, whether it's in the aircraft industry, the automotive industry, you're trying to lift something with a crane, all you really need is your periodic table and a couple knowledge of crystal structures, and you can figure out how much something weighs. So for this portion of the lecture, I'm going to end up with some of the takeaways. I want you to know what the different interatomic bondings, the ionic, covalent, and metallic, the crystal structures, mostly what the difference between crystalline and non-crystalline are, but these metallic crystal structures. I want you to know BCC, FCC, and HCP. I want you to be able to draw the reduced unit cell structure. I want you to know the coordination number, the atomic packing factor for each, and then be able to calculate that unit cell volume and then convert that into density. Some basic things to work on. So we know the crystal structures, and we're going to take advantage of knowing these crystal structures in the lectures to follow. So we're going to start looking at these unit cells a little more closely and start taking advantage of some of the other things we can grab from that. And we're going to find some really important things like atom locations, atom directions, atom planes that are going to become even more critical when we start talking about deformation and mechanical properties and other properties that may be available.